be able to review it. But in the meantime, if you have any doubts, you can ask. You can ask now. This here. Okay, you can also ask doubts about earlier stuff, right? So I think we just yeah, you can ask questions and clarify any doubts anytime during the lecture. Okay, so if there are no outstanding things, let's refresh our memory of what we were doing yesterday, right? So we were looking at the stack machine, and so what we wanted to say is that if you interpret the program, then the result would be the same as running the program after compilation, right? So this is what we want to show in this theorem, and we are and here's the theorem, right? If you run the compiled program, right, under the valuation v with an empty stack, then that's the same as interpreting the program, right? Maybe I'll just do this one. It's the same as interpreting the program, and because when you run the program, what you'll be left with is a stack, right? And the only value that is left on the stack will be the result of interpreting the program. So that's why, in order to match the types on both sides, so run will return a list of natural numbers, right? So hence we say, okay, you interpret it, and then you just make it a singleton list with that value. Okay, so this is what we are going to prove, right? In order to prove it, actually you need to prove a separate lemma, right? Which talks about something very similar, except that what this lemma says is similar to what is expected. So let's just look at the lemma, right? So it says that for all expressions, valuations, any list of instructions is and given a stack, right? If you run the program, and what program are you running? You're compiling E, this expression, right? And then you prefix it to this arbitrary list of instructions, right? And you're running this program, the compiled program list of instructions under valuation V on some stack. This might be any stack at all, right? What you are claiming is that you will have the same behavior as running this arbitrary list of instructions, right, under this valuation. Essentially, what you are claiming is that the compilation here, right, the compile of E produces a list of instructions and leaves a value on the stack. And you can capture that effect by simply interpreting it and pushing it on the top of the stack. Okay. So you have a compile E here, which produces a list of instructions, and you append it to the front of this arbitrary list of instructions. And you want to claim that instead of compiling and running it, we know that it is going to give you a single value, right? If you interpret that expression, it is going to give you a single natural number as a result. And the effect of doing this is the same as simply interpreting E under V. You interpret that expression under the same V, and then you cons it to the stack, this arbitrary stack, right? And the effect is the same. So we have a run here, we have a run here. All you've done is you've taken this compile E here, and instead of doing compilation, we are saying you can just interpret it and push it to the top of the stack. Right? This is necessary because of the way the induction is going to work. So as we see the inductive case, you will understand the reason why we want this lemma, right? And we are going to sort of, this is the workhorse for the actual theorem that we want to prove, this compilation. But we'll see why this is in fact the case. This is intuitively true, right? We are essentially claiming the same thing. If you run this compiled program, then it is the same as interpreting that, except that instead of just saying the stack is nil here, we are saying that it can be run on arbitrary stack. It can also have arbitrary set of instructions underneath. And this is useful because of the way the induction hypothesis is going to appear. Let's look at what this is going to be. So in order to prove this lemma, you perform induction on E, because we simply induct on E, and then we are going to apply the induction hypothesis on the subterms, right? And we simplify. So we get 5 sub goals, right? Let me make this bigger. And this corresponds to the 5 terms that we have here, right? Some of these are simple, right? So this goes off with equality. Constant and variables are just going to go off with equality, because they are syntactically the same expressions on both sides. The interesting reason why we actually wanted to prove this separate lemma appears here, right? The induction hypothesis that you have for, say, addition, right, says something about compilation of the sub-expressions E1 and E2, right? Because that is how we've defined compilation for addition. So we said if you want to compile addition, you compile E1, right? You compile E2, and then you add this addition instruction to the end of the instruction list, and you are going to get induction hypothesis for E1 and E2, right? And we have the induction hypothesis for E1 and E2, and what this says is this just the same lemma, right? But applied to E1. So it says if you compile E1 and do this, put this in part of this instruction list and run it, it's the same as running the rest of the instruction list IS here, and interpreting E1 under V. So we have the same for E2 as well. And this is useful because we see a similar structure here, right? We see compile E1, compile E2. And as we've done so far, right, what we've done is we have to sort of use the induction hypothesis in order to rewrite the term. But if you sort of observe what is happening here, right, just look at the term here for the induction hypothesis IHE1. So IHE1 says something about compile E1 appended to arbitrary list of instructions, right? I want to do this rewrite for compile E1, but if you look at the structure of the instructions here, right, the parenthesis is all not in the right position, right? So we know append is going to be associative, but really what we want is that we want the parenthesis to be just compile E1 on the outside, and the rest of the whole things, right, compile E2, add, and IS should be on the right hand side of the parenthesis, so that it matches with the structure that is expected here in order to apply the induction hypothesis. Observe that IS itself is a for all, right? It could be arbitrary. And all it says is that if you happen to have a list of instructions where the first term happens to be the result of compilation of E1, and second term could be arbitrary, and you append these two terms, right? So what we have to do is to rewrite this particular term so that it appears the same as this one. And how do we do this? We have to sort of search for we have to essentially apply associativity of append, right? And we've seen the search technique earlier in the lecture. And what we are doing here is that I'm going to search a rewrite for associativity of append, right? So I'm saying, okay, give me all the theorems that you have in the standard library, which will have this structure, this associativity, right? So A append to B, append to C. And if you search rewrite, you will get this particular theorem, which is what we want. So if you have a L plus M plus N, we can rewrite it as L plus M plus N. So there is an implicit bracket which Coq doesn't display here, right? So this is precisely what we want, so that we can rewrite this whole term, right? So that compile E1 comes to the outside, right? When you rewrite application is associative in reverse, right? Observe what happens. So now this associativity has been applied. So you get the compile E1 as the first term, right? And some term here, actually we don't care what this term is, because we can apply the induction hypothesis, because IS is a universally quantified variable, right? And now we can apply the rewrite. Rewrite correctly instantiates the IS here for us, right? When you apply rewrite, it knows that, okay, this is the term for which I'm going to instantiate for this IS. So if you do IHE1 now, observe that what has happened between here and here is that this interp E1 appears on this stack, right? Which is precisely what is promised by the induction hypothesis. So all we've done is we've cleverly applied this associativity lemma for append in order to be able to apply the induction hypothesis, right? And similar story for the rest of all of the proof, right? We have a similar story here, right? We have compile E2, append to add, appended to IS. Really, compile E2, this induction hypothesis can only be applied if compile E2 is on the outside. So again, we apply association is append associativity is in reverse, right? So you get compile E2 plus there is an implicit bracket here which is not shown. So now this term matches what is expected to apply this induction hypothesis, right? So you can apply the induction hypothesis now. This goes through. And now what we have is just the add on top, right? And if you look at the definition of run function, it will show you that if you have an add at the front, then you sort of pop out two elements from the stack, add that and push the result into the head of the stack, right? And this can be, because this is part of the definition, you can just do simplification. And once you simplify, observe that these two terms are the same, right? And the proof goes through. The rest of the proof is also using the same reasoning as the parts over here, right? The same for subtraction and multiplication. So if you keep applying the same thing, the whole proof goes through. So what we've done is that we proved this more general lemma, which holds for all instructions which are suffixes, right? And all stacks. And we are going to apply this particular instance for proving our theorem. And the idea here is that the instruction list, the tail of the instruction list is going to be nil, right? There is no instruction list. And the stack is going to be nil as well. So the theorem that we want to prove is a specialization of the lemma that we've actually proved. So all we need to do is to ensure that we modify this term suitably so that we can apply the lemma directly. So, okay, so here's the theorem. We can do simplification just to simplification simply pushes the universally quantified variables to the hypothesis. So simplify also does the work of doing intros, right? Simplify is from Frap library. Simple, which is what we had used in the very early lectures, that just does simplification, right? By looking at the definition, this is a bit overload, right? And now, if you look at this particular term here, right? So it has a empty list here, so which can be instantiated for stack here, right? And because stack is empty, you will get a singleton list here, which is fine. But observe that the term here, right, says it's compile appended to some IS, right? But you only have compile here. So syntactically, because we are operating everything syntactically, right? We know that you can rewrite this term as compile appended to an empty list, right? If you rewrite this term as compile appended to empty list, semantically that's the same thing, but syntactically this will match the term that we expect here in the lemma. So we have to do this rewrite in order to help Coq to be able to apply this lemma, and we need to search for a theorem, right, which says appending arbitrary things to an empty list gives us the same empty list. So if you search rewrite for this one, so observe that we have append nil end. It says that for any term, right, any type and any list L, L is the same as L appended to empty list. So why do we need this? We need it so that we rewrite this to compile E plus an empty list so that it matches the lemma there. We do the rewrite with the particular instantiation, right? We say rewrite this. So this this tactic here, right, which we are going to apply here, which is apnil end. Sorry, not tactic. The term that we are going to use to rewrite takes the implicit variable here, right? Implicit argument here, which is the type, and then it takes an explicit argument, which is the list. So we explicitly instantiate it to compile E, right? And the reason is that if you don't do this, it will rewrite at the wrong position. So I'm not going to show it. It is up to you to just drop this argument, right? And then see where it rewrites. It will rewrite at the wrong position, and that is not what you want. So because the way you read for all is also implication, right? Uh, sorry, for all is also a function. So when you have for all quantified variables, you can always treat that as a function that you apply. So we instantiate that argument here explicitly. So by supplying the first argument, this is instantiated, right? So you get a particular instance of this lemma, which is specialized to compile. And when you do this rewrite, we now, so this is before the rewrite and after the rewrite. Observe here. So we just have this append to null. So once you have this, then you can directly apply this lemma, right? So you have IS, you have an empty list, right? And you have a stack, which is also empty, right? And now you can directly appeal to the lemma. And the way you do that is just apply the lemma, right? When you apply the lemma, the proof is done, right? And yeah, there was some ingenuity in the proof, right? But the real ingenuity in constructing theorems, right, is to know what lemma to prove, right? And that sort of comes with practice. I'm not going to say there's a magic there's a magic formula which you can apply everywhere. And really doing intelligent proofs is coming up with useful lemmas. So what we will do, in order to train you up in this, what we'll do is we'll sort of have more open-ended problems as we go through, right? But I will sort of suggest lemmas that you can use. You might choose to not use it, but as we go along, I will not provide the lemmas, and I would expect you to come up with the right lemma to prove it. I mean, you can come up with arbitrary lemmas to prove it. You can also do it however you want, right? But coming up with one way of proving it is sort of the technical challenge. That is sort of the art in program verification. Coming up with the right lemma so that you can apply the induction hypothesis properly. Okay, so that is what I wanted to say about the stack machine. Any questions on this so far? Okay, so if there are no questions, let's continue. So let's get a bit fancier, right? So we've been doing simple arithmetic expression language. That's fine. We've also had evaluation. Really, we want to get to a world where we can prove things about imperative programs as well, right? I want to prove things about C-like languages or Java-like languages. So let's define a small imperative language, right? And the language has just a few things, right? It has constants, it has variables, it has expressions. The whole expression language that we saw earlier is still there, right? But we also have a command language. And the command language, you can sort of think about a very small imperative language, right? There is a command called skip, which has no effect. It's like a no op, right? And there is an assignment to a variable, right? You can evaluate an expression and then assign it to a variable, right? This is like what we do in imperative languages, right? We say some x equals 5. This is assignment. You have sequencing, so you can take two commands and then sequence them together. And then we have repeat. So repeat E, do C, done, repeats this command, right? E number of times. So E is an arithmetic expression, right? So it will be, when you interpret E, it will yield you some number, right? And you just perform this command n number of times. So the the one thing that I want to mention here is that this is not a Turing complete language, right? This is still, you cannot write infinite programs here, because this E is always going to be sort of some n, right? You cannot write infinite loops here because it reduces to an n, and you only apply this command n times. You cannot represent infinite loops in this simple language. So we can still describe the semantics of this language as a fixed point, right? So it's a very conscious choice what we are doing here. We are not putting arbitrary, it's not like a while is what you need to remember here. This is not like a while loop which is checking for some arbitrary condition, right? We actually just have a E, right? And that is going to be some natural number, and we are going to repeat this command so many times. Okay, so that's the command language, right? That we've sort of added on top of the expression language. So how do we now have to give semantics for this language, right? And in order to interpret this repeat expression, the way we sort of think about this is I have this is going to be evaluated to some natural number n, right? And the meaning is that I'm going to apply this command n times. Right. So in order to help with that, here is a simple definition that I'm going to use. I'm going to use f raised to 0 as applying f 0 times on some input, right? So if you apply some arbitrary function 0 times on that input, it's the same as the identity function, right? You get an input, you're going to apply the function 0 times, which means that the value is going to be the same as the input. So that's the identity function, right? If you want to apply some function n plus 1 times on an input, then it's the same as applying that function n times on an input. And this is function composition. It just says one more time, right? We are just splitting that apart just once. So all I'm saying is that I have this helper function that is going to get me a way of applying a particular function n times over some input. Okay, so I have this helper definition on the side. So let's now look at the how we interpret the command language, right? We know how to interpret the expression language. Let's look at the command language. So we interpret skip. So this command language is going to, unlike earlier examples, right? This arithmetic expression language resulted you in a single natural number as a result. Okay, and then this language, which was the target of the compilation. So it was going to result in a stack, right? It had an input stack. It might be nil, but when you run the program, what you end up with is just a stack, right? And we also proved that if that compiled program comes from the expression language, then the stack will have exactly one element at the end. So that is fine. So the way this particular command language is going to work is that it is going to, the result of executing this programs in this imperative language is a valuation, right? So it is going to take some input valuation. A valuation is just a map from variables to natural numbers. And what you're going to get as a result is the target valuation. So you're going to execute the command and you'll just get some valuation as a result. Why do we do this? Because I want to give semantics for saying simple program, right? Which is I set x to 1 and y to 0. So the meaning of this program is fully captured by the valuation at the end. If you start with an empty valuation, the valuation will have x equals 1 and y equals 0. That is what I want to capture. So you can sort of think about the interpreter for this command language as a value transformer, valuation transformer. So it takes in an input valuation, takes in the program that you're going to execute, and what it returns is another valuation. That is a map of variables to values again. Okay. So with that, what is the meaning of these commands? So if it is just a skip, you're not going to do anything, right? You take the input valuation, you just simply return the output as the same valuation. If you assign x to e, right, under this valuation v. The meaning of that is this new valuation where you extend the binding for x with the result of interpreting e. Observe that interpreting e is the same as what we have seen previously, right? E is one of these things, right? When you interpret e, you just get a natural number as a result. And all we say is that when you bind something like this, when you set x equals 1, you take the input valuation, right? And then you extend it with x to 1, is what we are saying here. And when you have sequencing, you naturally follow along the structure of the sequence, right? You first interpret C1, right, in the input valuation V, that is going to return another valuation as a result. You interpret C2 under that result valuation, okay? And then repeat is a bit interesting. So what is repeat going to do? It's going to repeat the command E times, right? By E, I just mean the result of interpreting E. And that is precisely what we have here. So the way to read this is that you interpret C, right, raised to whatever the result of interpreting E is going to be. So this raised to meaning is defined here, right? If E is going to evaluate to 10, then it is the same as interpreting C 10 times under V. So you're going to execute that that command, like command or a list of commands, 10 times, right, in the input valuation. So you simply keep passing that valuation through, right? You execute once, you'll get a valuation out. You execute more times, you'll just get a valuation out. And you keep doing this until you get the valuation finally. So that's the meaning of this syntax here, right? The syntax here precisely is defined thanks to this self-composition. Okay, so any questions on how these commands work? Okay, no questions. In which case we can proceed. Yeah, okay. It is suspicious that I'm not hearing any questions, but okay, you have a think about it and then come with questions in the next class, right? If I keep talking myself, I think it's not fun for me and fun for the listeners, right? If there is interaction, I would really like it. Okay, so anyway, so as we did in the previous lectures, what we are going to do is to take this and encode this in POC, right? And here is how we do it. Yeah, so we define the command language, right? So it has skip, assignment, which takes a variable on the left, and this is the right hand side, right? Some arithmetic expression. Sequence is sequence of two commands, and repeat takes an arithmetic expression, and it has a body, right? It's like a loop that has a body, and the body is also a command. So now we want to describe this self composition, right? Applying a particular function n number of times. So that is what we do here. So this is the function that we want to apply. It's going to be an A to A function because it is going to be self-application. So it must be the case that the input matches the output. We are going to apply this function n number of times, and we are just going to get a function as a result. I mean, this is higher order, but you can also write it in first order. The details are not that important here. So how does this work? If n is 0, then we are just returning the identity function, right? Which is the same as what we have here. If it is n plus 1, then it is the same as self-composing the function n times, right? And then composing it once more. So you do one more application of f of x, and then recursively call this to apply n times. And this is the input that eventually will come, right? Because we say the output is alpha to alpha, we define, we explicitly take a argument here. And that's the argument that we apply this function on. Okay, that's the same as this one here, right? So this is once and this is n times, right? And you get n plus 1. So this is once, this is n times, so you get n plus 1. So that's self-composition, right? Yeah, okay. And then we actually give a fixed point, an interpreter for the execution. As I mentioned, the way to think about this execution, right? This interpreter for this command language as a valuation transformer. So it takes a command as an input, it takes a valuation, and then returns a valuation that sort of captures the effect of running this program, right? So if this is this is the same as what we have here, right? So if it is skip, then you return the input valuation. If it is assignment, then extend the valuation with this binding, key value binding. If it is sequence, then first do C1, then do C2 on this valuation V. If it is repeat, then apply self-composition on the body, right? On the execution of body. So when you exec body, body is the command, right? When you apply exec on body, you are applying exec on some command. So you get a function which is a valuation to valuation, right? We are partially applying exec here. So this is a valuation to valuation function, right? And when you interpret E in V, you get a natural number as a result, right? And all we are saying now is that self-compose this valuation to valuation function, which is the result of executing the body once, right? N number of times, right? And the initial input is V, right? That's the initial input that comes from here. Okay, so that's the fixed point definition. That's the same as what we have here. Okay, what can we do with this program now, right? We can actually write pretty interesting programs already. So we can write the factorial function, which you might write in C, right? So here is the factorial function, right? So and because of the way we've set it up, right, we don't have inputs and outputs to functions. We just have valuations. So we set the output to 1 initially, and then we have a repeat loop that repeats the body input number of times. And in the body of the input, what we do is we simply do output is output times input, right? And input is input minus 1. So we keep doing this. So as a result, what would happen is that the input will become 0. Actually, it doesn't matter, right? So it is not necessary that this line is even there, because this input is interpreted when you actually execute the repeat. So it is decided that you're going to execute n number of times. So this is just there for the sake of completion. So just so that we execute it n number of times, and when this loop completes, right, input will be 0, right, because it is running for input number of times, and output will have the factorial of the input, because output started at 1, and you keep multiplying inputs over and over, so you get factorial as a result in the output, right? This is sort of
Sir,
the
I can't understand the self-compose function. Can you
oh, this
explain it again?
yeah, okay. So this function is sort of taking. So what's the point of this function, right? The point of this function is I'll give you some function f, right, and I will give you a natural number. And what I want as a result is the application of this function n times over some input, right? Um, and what we do is we sort of say, I mean, it is written in this weird way, but you can sort of imagine writing it in OCaml this way, right? So you can also write it as let rec self compose. You take an f, you take an n, and then there is some input v, right? So um, if n equals 0, then you just return v, right? Else you do self compose f of n minus 1, of v, right? So does this function make sense? So what we're doing is if n is 0, then we return v, right? If n is greater than 0, then we recursively call this function with the same f, n minus 1, and we apply f1v once. Does this make sense, Akash?
Sir, but how does this translate to the self-composing Coq? There is no V in this function.
Yeah, so what we're doing here is that you can drop this v, right? If you don't get this v, then I have to return the same v here, right? So we can write this as fun v arrow v. So whatever v you get, you just return the same v. Okay,
Yes.
and yeah, so that's yeah, and the point is because this is um, returning a function as a result, right? So you have to sort of also do fun v arrow this thing. Does that make sense, Akash?
Yes, sir. Yes.
Yeah, so it's just a weird way of writing it. Doesn't matter. So you could have written it this way as well. Both are equivalent, right? Both functions are the same, doing the same thing. Okay, so that's thanks for asking a question, Akash. Right, so I'm glad you sort of stopped and asked questions. Please do ask questions, right? Otherwise, it's I don't even see you, so it's a bit it's like I'm talking to myself, which is bad. Okay, so where were we? We were here, right? We were looking at the factorial definition. This is what we want to write, but because we are dealing with abstract syntax, right? The same function would look like this, a bit ugly. So essentially, it says, okay, a sequence of assign output to 1, repeat of variable input, then sequence of this sequence is sort of capturing this sequence here. Assign output is output times input, and assign input is input minus 1, right? This is sort of quite ugly. It's very hard to read. So Coq has this expressive way of adding concrete syntax. So this is abstract syntax, right? And you can also add concrete syntax that sort of translates to abstract syntax automatically. I'm not going to explain how this works. These are sort of not particularly interesting, and they are not doing much. So if you want, you can sort of look at them in detail and reverse engineer what is happening. All it has to do with is uh, defining the actual syntax and then defining what the precedence level for the operators should be. But anyway, I'm going to skip that. But what we are going to get is that we are able to now write the program in the syntax that we would like. So, so this is very close to what we write here, right? Output is output, out, assign 1 to output and so on. So here is how you do it. Assign 1 to output, repeat input, output is output times input, and input is input minus 1, done. So I have repeat doing done as the syntax for this repeat loop. So now we can at least read the program that we are writing. So that's the factorial function. So, okay, so we've defined the factorial function. We can execute it and get the results out. But what would be nice, I mean, because we are doing program verification, right? You defined the imperative language for doing factorial, and we know how to do functional way of writing factorial, right? The mathematical notation that uses recursion. I want to prove that this implementation is correct with respect to the functional definition of factorial, right? So we know this, right? We've written. I mean, these are sort of we learned this imperative way of writing things in C, right? When we write our first C program, this is one of like the very first things that we use to explain loops. So, but we've never sort of I mean, we sort of take it for granted that, okay, I have the specification in mind, I just have to write it, and this is correct. But what program verification lets you do, I mean, we are not doing C, but we are sort of doing it in a variant of C. is that we can actually prove, right, that this mathematical implementation is the same as the language that you define, which has imperative features. So, and of course, it's good that we are not doing it in when we are learning C, because the um, the naturally what we are doing when we are translating these programs in our mind to imperative language is enormous amount of work, right? And it will show up in the proofs. Um, so the bulk of the proof, right, in order to show that this specification of factorial is the same as this implementation, involves proving things about the body of the factorial, how the body sort of changes the input and output as it executes. So what we have here is just the definition of factorial body, and the body is just these two statements, right? So output is output times input, and input is input minus one. And we are going to write a lemma and prove by induction some property about the body. Okay, so we are going to do that. And then what we're going to do is to use this lemma in proving the full implementation, right? So most challenging part of any of these proofs, right, is setting up the intermediate lemma so that you can apply induction in a proper form. So that is what we are doing here. And in this particular case, it happens to be proving some property about the body of the program. Okay. So we have the body here, and the property that we want to prove is given here, right? So we have this lemma. So what does this lemma say? It says factorial OK prime, and it is going to prove some property about the body. In particular, it says that the self-composition of the body semantics produces the expected value of the valuation. What do I mean by this? It says that assume for all inputs, right, some input, for all output, some output, right, and for some valuation v, if the valuation has a binding for v, which is the same as some input, right, and the valuation has some binding for output, which is the same as the output variable that I have here, right, we are sort of saying the valuation should have the right expected bindings, right. Then if you um, execute the factorial body, right, n number of input number of times, and how do we represent that by self-composition, right? If you execute the body input number of times on the valuation v here, right, what you will get out is a valuation, right? And that valuation, in that valuation, input will be zero, right? Input will be zero there in that valuation, and the output will be output times fact of input, right? So this is interesting because we started with arbitrary output initially, and in the actual program we are going to have output is one, but we are saying for all outputs, if you execute the factorial body, then it is the case that the output that you will get is the factorial of input, because that is what we are multiplying here, right? This is the statement there. And if the output is not one, then the result that you will get will be multiplied by that output value. Okay, so this is the property that we want to prove about the body, and what we will do uh, for the actual theorem that we want to prove is that we will set the initial output to one, right? And naturally, then this particular thing will reduce down to factorial of input. So that's what we are going to do. So we are going to prove this by induction on the input, right? So what if input is 0? What if input is n plus 1? So let me move it here. This is going to produce a large term, be warned, right? But we will work through it. So we are going to induct on input and simplify, right? So first thing, we've done simplification. We got two goals because of the preconditions that we have here, right? So simplification made one of the things simplified, but we get two sub goals, right? First thing that we want to show is that the assumptions that we have about the valuation containing the input values, right, is actually true. and it holds true when the input is 0, right? So what does it say? I want to show that v is the same as v extended with input is 0, right? And the output is output times 1, assuming that if you look up in v, that input is some 0 and the output is some output, right? This seems obvious, right? Because if v already has input is 0 and output is some output, then it must be the case that these two maps are equal, because all I'm saying is that I'm extending the map with input is 0 and output is output times 1. But we are now obligated to show that these two maps are in fact equal, right? And as I mentioned before, these maps are sort of special creatures in Coq, right? They are not computable. They're not like a list which you can destruct and show that everything is the same. But thanks to how they are organized, we have a nice tactic to show that two maps are equal, right? And the tactic is called maps equal, right? And maps equal is a tactic that essentially says that if you want to show that two maps are equal, you show that all of the relevant keys have the same values, right? So if you apply maps equal, you get a few more sub goals, and the goals say that show me that if I look up output, right, in this original v, then it is the same as some output times 1. We know if we look up output in v, we are going to get some output, right? But we just have output times 1 here, so we know it is true. So we can rewrite this with h0, right? So that we get some output on the left hand side. And now I want to show these two terms, but are equal. But I have the sum constructor that is sitting outside. As we saw in, I think, the previous end of the previous lecture, there is this tactic which is called f equal, which says something about equality of functions, right? So if you want to show that f of x equals f of y, it is enough to show that x equals y, right? So we apply f equal, and then it now obligates us to show that output is equal to output times 1, and linear arithmetic makes it go through. Linear arithmetic works here because this is multiplication by a constant, right? Ring also works here. Just to yeah, you can also use ring here. So linear arithmetic makes it go through. And for the second one, we just have this as an assumption, right? So here's the thing that we want to prove. Here is the assumption. So I can use the assumption tactic, but I can also use equality. Equality also does these assumptions. I mean, looks at the hypothesis, and if assumptions are directly there, it uses it, right? So equality makes this go through. Okay, so now we have this large term, right? So this is sort of the first non-trivial thing that you will come across. So there is something large going on here, right? But a key part of operating with Coq is that it might throw large terms at us, but you have to sort of identify patterns here, right? So observe that there is a self-compose and there is this huge term here, right? And then input v equals something. That's part of the induction hypothesis. Observe that we have the same self-compose here, right? We have self-compose all the way to here. There is some input, and the term here is the output, right? The term here is the input to the self-compose, right? That's the v argument here, right? So there is some structure that is the same in the induction hypothesis and the conclusion that we want to show, right? And there is on the right hand side some v extended with input and output, right? And similarly, we have v extended with some input and some output. This output is different from the output term here, but that's okay, right? If you sort of look at where this output variable comes from, it is a for all quantified variable. So if you find a particular value that you can substitute for this output, so that the term matches this term, then you can apply the induction hypothesis. So that's the trick there, right? Observe what are the for all quantified variables, so that you can apply the induction hypothesis. So here this v is a universally quantified variable, right? And output is also a universally quantified variable. And similarly, here there is some v, right? Right, there is this v which goes all the way up to here, right? The brackets say that this goes all the way up to here, but it's okay because in the induction hypothesis, this happens to be universally quantified, right? So the first thing that we do, right, is that we observe that there are two hypotheses which say something about looking up input in V and output in V, and it gives us the value for those, right? And if you also look at the definition here, right, we have looking up output in V, looking up input in V. So first thing we are going to do is to actually do this rewrite. So we are going to rewrite both H and H0 in this definition, right? So we can rewrite both of those. Observe that I'm actually rewriting two hypotheses in the same command. This is just a convenience thing, right? So so you can also rewrite it individually. So that's fine. So now it's a bit simpler, but it's still large. But the key thing to recognize here, right, is that as I mentioned, this output is universally quantified. This V is universally quantified, right? I have an output here, right? A V here, and similarly, I have this output is some large term, right? It's some term. This V is this term here. Um, this V is the term here, right? So the clever bit that we are going to do here is that we are going to instantiate this output, right, with the concrete term so that it matches the expected term here, right? The expected term here is this one, right? Output times fact of input plus input times fact of input. But what you have here is output times fact of input. But again, output is a universally quantified variable. So you can substitute for this output variable something so that it syntactically matches this term here, right? So what is that instantiation? That instantiation happens to be output times input plus one, or one plus input, right? Why is this the case, right? I magically picked this value here. Why did I pick that? You can be a little bit careful, right? So and then observe what is happening. So let's just take this term, right? And because we have output here and the concrete value of output also here, right? It's a bit confusing because one is actually a universally quantified variable. So this output comes from here, and this is like some arbitrary output that is a natural number. I don't want to confuse this, so I'm going to say rename this as O, right? I'm just going to walk through this example just to show what is happening. So what do we have here? So we have output times fact of input, and I'm going to rename this output to O. So I have O times fact of input. And what I'm substituting here is output times 1 plus input, right? I'm going to substitute for O output times 1 plus input, right? And I get this term. And I'm going to distribute this multiplication, right, over this addition. So what do I get? I get output times fact of input plus input times fact of input, right? That is just distributing this multiplication over addition. And if you look at this term now, right, this is the same as the term here, output times fact of input plus input times fact of input, right? All we've done with this clever instantiation of the induction, the universally quantified variable in the induction hypothesis is that we've made the right-hand side, right? The output term in the right-hand side the same. So that is the reason why we particularly instantiated with a concrete value, right? Once you do this instantiation, right, what happens is that you still have this large term, right? But we've applied the induction hypothesis. We are no longer going to apply the induction hypothesis. It is no longer needed. So there is this nice tactic called clear, right? Which just deletes a hypothesis from the set of assumptions so that it is a bit more readable. So all I'm doing is that I'm clearing the induction hypothesis IH input, which is this large term here. I know I'm not going to use it, so I'm just going to clear it just to see, just to add more clarity. So again, recall that all is going to apply, all is a tactical that applies a particular tactic on all of the subgoals. So that's what I've done here, right? So I cleared the input, IH input hypothesis from all of the subgoals. So that's done. Now you see it's very simple, right? So if you just look at this very closely, right? So what do I have here? I have V, I have input is 0, and output is output times fact of input plus input times fact of input. But here I have V, right? I have a binding for output, I have a binding for input, but I also have an outer binding for output, input, and an outer binding for output. Because these maps are extensional, right? And what I told you in the last class is that if you extend a map with binding for x is 1 and then binding for x is 2, if you look up in the final map what the value of x is, it is going to come from outside in, right? Because it comes from outside in, you're going to get x is 2. So the fact that these bindings are there doesn't matter because they are shadowed by the outer bindings here. So if you ignore this, right, the maps are going to be equal, right? And that is the intuition that we are going to use. We are just going to say, I know these maps are equal. Let me prove that the maps are equal. So you get some obligations, right? And if you apply f equal, this sum constructor goes away, and then it is just a it's just a linear, it's just a ring tactic, right? So you're just multiplying. This is 1 plus input. So you distribute multiplication over addition, you get this term. So you can apply f equal and then ring to make it go through. Okay, so that sub goal is done. And then for this one, all we have is that we have to show that the result is some input on this map, right? If you look up input, right, in this map, the map is defined here. Oops, map is defined here, right? And because this is a lookup, you can just do simplification because we know something about this, and simplification just tells us the obvious one, right? So it simplifies to very simple obligation, which is you apply f equal, that goes away, and then linear arithmetic makes it go through. And the last one is also very similar. So you're looking up the output variable and you're saying something about the output variable. So if you simplify, you get the obvious looking conclusion. So equality makes it go through. So all you've done is we've proved some property about the body of the factorial, how the body of the factorial changes the output and the input values, right? Assuming some output and some input, when you execute the body input number of times, what you'll be left with is input is 0 and output contains output times fact of input. Now, as I mentioned earlier, right? So if you want to show that factorial is okay, which means the imperative version has um, same semantics as the functional version, then you assume that there is some input, right, in the valuation, input valuation, some input. If you execute the factorial program under this valuation and you look up the output value, then that value is going to be some factorial of input, right? So this is the obvious theorem that we want to show. So you simplify, which also quantifies all the variables, right? And there is some information about what is the value of initial value of input. So you apply that as a rewrite, right? And then what you have here is just an expanded version of the factorial OK, right? This factorial OK thing that is that we've defined previously, where we are going to sort of say the input is one and output is, sorry, the input is input and output is one, because in order to prove this, we are not going to assume it on arbitrary output. We are going to assume that the input is going to be, sorry, the output is initially going to be one and the input is going to be input. So if you apply the rewrite by directly calling to that lemma and you simplify, you get very simple goals to prove after that. So this is f equals and linear arithmetic, because it's just an addition. And these two are simply equality. So this is assumption and this is equality, right? So so we have proved that the imperative version of the factorial works just like has the same semantics as the purely functional recursive definition, right? And the key takeaway here is that whenever you come across loops, right, and that is the point where some induction hypothesis is necessary. And as we will see in later lectures as well, loops are the places where things get really complicated, because you want some invariant about um, the execution of the loop, right? Um, and and all we did, the clever bit that we did here is that we sort of captured the meaning of executing the loop, right, using this separate lemma, and we directly applied it in the main theorem. Right? So actually, I have taken too much time. I'll stop here, and then we can catch up next week. I just have a little more things to do in this lecture, but I'll release the next set of assignments today. And I apologize that it was a bit tedious with writing the intuition for a lot of the questions, but think of it as TDM that is worthwhile, right? So it'll be tedious this time. For the rest of the lectures, I won't ask you to write the intuition, but I hope that this would have trained you enough to actually apply it naturally, right, in the next lecture, in the next assignment. So you won't have to do any of that. You just have to prove theorems from the next assignment onwards. I will release it today, and then it will be, the deadline will be next Friday. So I'll stop here. I've taken too much time. Apologies for taking too much time. I'll catch up next week then. Good luck with the assignment, and hopefully it'll be more fun, not tedium, going forward. Thanks.